we do last week? We looked at two things, the Kraft-Macmillan inequality and the asymptotic equipartition property. So if we remember, we talked about the different types of codes we might be interested in, particularly uniquely decodable codes and prefix codes. And remember, what's a uniquely decodable code? It's where when I give you a sequence of outputs concatenated together with no commas between them, you can still figure out what the original input is. But uniquely decodable codes are a pain because they're hard to manipulate. And so we have prefix codes or prefix-free codes, which says no code word can be a prefix of any other code word. So you go through your code word and you, as you're going through, you hit a point and you go, okay, I've got something which is a code word. If you've got a prefix code, you know you can stop. You know that's the input you had because this code word can't be the prefix of anything else. There's nothing that you could see later which would change what this initial segment refers to. And so prefix codes are easy, and the Kraft-Macmillan inequality says if a basic inequality, the Kraft-Macmillan inequality, is satisfied, then there exists a prefix code with those code word lengths. And conversely, if you give me any uniquely decodable code, the Kraft-Macmillan inequality must be satisfied. So we have this simple dichotomy which says, well, we don't need to worry about uniquely decodable codes. We can focus our attention on prefix codes, and we're not going to lose any efficiency. The other thing we talked about was the asymptotic equipartition property, which says if I've got a sequence of IID random variables, then I may not be able to say very much about a single element, a single output, but if I look at a long string, then the law of large numbers kicks in. And it means that when I've got a long string, I can separate the world into two classes, one being the typical sequences that I'll typically see, and they happen with approximately equal probability, hence the term equipartition. They're about the same probability for every typical sequence. And then there's other sequences which occur with low probability. And we get this dichotomy between them. And so this is something which holds in the limit, but we get this tolerance statement about talking about typical sequences up to some error level. What are we going to do now? Well, we're going to try and put these things to work to talk about some optimal ways of coding. So optimal codes. Okay, so we should really define what we mean by optimal. So definition, we call a symbol code C. So what is C? What's a symbol code? Well, remember, it takes all the input symbols, which are things in X. It maps them to strings in Y, so sequences of output symbols. Okay, we call this optimal for a random variable X with probability mass function P, but we're not going to explicitly write that down. Where X is a finite set, Y is a finite set, etc., the usual setup. If it minimizes the expected length of the code word associated with X. So what am I saying? I take the random input, I evaluate the code word on it, I calculate the length of that code word, and then that's a random variable because the input was random. Its distribution comes from the distribution of X, and so I take the average. And on average, I should minimize the length of the code word that I get out from a single input. So I put in an input of input X, I look at the average code word length I get out. If I've minimized that on average, then I have an optimal code word. But we should be careful among all uniquely decodable codes. C prime. So this is really C prime. It minimizes. We'll put the prime here because we're minimizing this with respect to C prime. where C prime is a UD code on our space. Okay, otherwise it's very easy. You just map everything to 0. That minimizes the code word length. But it's a useless code, you can't figure out what you put in. So we have to restrict to uniquely decodable codes. But that's actually not too bad for us, because we have the Kraft-Macmillan inequality, which we know must hold. So let's sketch out what we can say roughly about this. So I'll move on to the next board. So from Kraft-Macmillan, a code is optimal if it solves the constraint minimization problem with code word lengths Cxi equals Lx. So if I give you a possible value, that's the code word length, same notation as we used in the Kraft-Macmillan inequality. So we're trying to minimize the expected code word length. So this is the sum over x's in my input space, probability of x times L of x. That's the average code word length. That's the thing I'm trying to minimize. But I know that I have this restriction to uniquely decodable codes. But we know that anything that satisfies the Kraft-Macmillan inequality, we can construct a code with those code word lengths, and vice versa. So I can think of this just as a problem on code word lengths, minimize this subject to the Kraft-Macmillan inequality. So subject to, okay, so I need the Kraft-Macmillan inequality to hold. So it's the x's such that p of x is greater than 0. D to the minus L of x is less than or equal to 1. And, well, what do I know about the code word lengths? They're natural numbers. Okay, so we look at this and we can think about that problem. That is an integer programming problem. So I'm thinking, actually, I don't need to worry about finding an optimal code. I just need to find an optimal set of code word lengths. And then I can construct a code using the trick we showed in the proof of the Kraft-Macmillan inequality. So if I just try and find the optimal code word lengths, try to minimize the average length subject to this inequality and the fact that the code word lengths are integers. So this is integer programming. You can solve it. It's a pain. It's computationally quite tricky. But we can do something if we sort of forget that constraint. We can actually try and solve this thing in closed form, at least approximately, to give us some intuition. So ignoring the integer constraint and setting, so the best thing would be if I can make this exactly equal to 1, then I'm sort of using my code words fully. So let's relax, let's ignore that constraint and let's set this equal to 1 just to make our lives easier. So the sum d to the minus Lx equals 1. So if I do those, now I've got a problem I can actually solve. We can use Lagrange multipliers. Okay, so what's our Lagrange multiplier problem? So I want to minimize the sum over x of px Lx. And then so that's my objective. I need to introduce the constraint. So I put the Lagrange multiplier lambda. And what's my constraint? Well, I've got that the sum d to the minus Lx, sum over x, minus 1, this has to be equal to 0. Okay, so there's my Lagrange multiplier problem. Okay, so I want to optimize this with respect to Lx. Okay, setting derivatives in Lx and lambda to 0, we get Lx is equal to minus log of p of x. Okay, so you just differentiate this with respect to L. This term you just get p. This term you get the appropriate log term because you've got d to the minus L. You rearrange, set that to 0, and you get something that looks like this with a lambda there. And the lambda is going to come out and is dealt with by the fact that you know that the probability is summed to 1. Okay. So we need to check this is a minimum. So to check this is a minimum, we use convexity. So I'm not going to write it out, but the convexity comes because we know this sort of thing is nicely convex. You go through and you verify. You can use Gibbs inequality, Jensen's inequality, the same thing. Yes?
Yes, I assume that D is
2. Log D. There we are. So if we do this, this gives an average length. So I'm not going to do the check because I'm waving my hands at every step at this point. But if I do that, then what do I get? Well, the expected code word length should be approximately, well, the code word lengths are these. So x minus px log px, which is the entropy of x to the base d. So I get my entropy coming out in a fairly easy way. And that tells you that, okay, I've been a bit of a cheat. I've pretended that I can set this to 1. I've ignored the integer constraint. But if I do this, the best that I can hope for is to get the entropy out. The average code word length being the entropy. It's the best I could hope for. Okay, now that's a hand wave, but this is a mathematics course, so we actually want to prove it rather than just waving our hands. So let's do a theorem. Okay, and this is the source coding theorem. So let x be a random variable taking finite values, finite values in a set X, and C, a uniquely decodable D-array source code. Then the entropy to the base d of x is less than or equal to the expected value of c of x. Okay, and equality holds if and only if the code word associated with a value x has length exactly minus log to the base d of the probability that x equals x, and that has to be an integer. So if you can do this, then we can so if you have this, then you get an equality here. Otherwise, you know that the entropy is always a lower bound on the expected code word length. Okay, proof. So let's do it. Set Lx to be the length of the code word associated with x, and q of x to be d to the minus lx divided by the sum d to the minus l x prime, sum over x prime. Okay, so we notice that q is a probability distribution. It adds up to 1. All its terms are positive. So it is a probability distribution, which is sort of going to be close to the optimal thing if everything works out. If my probabilities were of this sort, then q would be exact. Okay. Use a new board. Big calculation. So then the expected code word length minus the entropy, or the d entropy. Well, let's just write out what these terms are. So this is the sum over x of px lx plus the sum px of log d px. Okay, that's just writing out what is going on. Let's rearrange this a little bit. Lx, I'm going to make this look more like this term. So it's the sum over x of px log to the base d of d to the minus lx, and I'll put a minus sign here, plus px log d px. Okay, so now I look at this. Well, this is the same as, so minus the sum px log to the base d of, well, that's the term that appeared in qx. So it's q of x times the sum d to the minus x prime plus the sum px log d of px. Okay. And I'm rearranging this so that I get Gibbs inequality helping me in the end. So I am going to now break this up into two terms. So minus the sum of px log to the base d of the sum over x prime d to the minus x prime plus px log, or keep the two sums separate, log d of px over qx. And that looks a lot like a divergence. In fact, it is exactly a divergence. So this is now minus, well, all of these terms are the same. This sum doesn't depend on x. So I've got the average of something not depending on x. The probabilities all sum to 1. So this is just this term here. So log to the base d of the sum over x prime, d to the minus x prime. That's just a constant. I can't do anything about it. When I'm minimizing, it's just going to hang around. What about this? Well, this term here is exactly the divergence to the base d of p against q. Where the divergence to the base d is the divergence where I use logs to the base d. And now you look at this and you say, hang on, what can we say? Well, Kraft-Macmillan tells me that this has to be less than 1, this term here. So log d is more than, the log of something less than 1 is less than 0. Negative sign, positive. Divergence, also positive. So that must be positive. Okay. But, okay, when could this be equal to 0? So I've proven the inequality that I want. If I look at my statement here, I've proven exactly this. When do I get equality? So equality requires, well, I've got the sum of two things which have to both be positive. So I need, first of all, that has to be 0, so this has to be 1. So the sum over x prime of d to the minus x prime equals 1. And this has to be 0. The only way the divergence can be 0 is p equals q. So if p equals q, that means p is precisely this thing, which is that statement there written slightly differently. Everyone happy?
Those are supposed to be Lx primes, right? Not
I'm sorry?
d to the minus Lx prime instead of like, what's that?
D to the, yes, L there, and L there, and L there, and L there. You're right, I'm just lazy. Happy? There we are. Okay, so that gives us a lower bound, which tells us the best we can hope for in our coding. We know we can't do better than getting an average length equal to the entropy, and we would have to be pretty lucky to get this, because we would need the real probabilities of our source to be exactly powers of d. And if they're exactly powers of d, then we're okay and we can do this exactly. Otherwise, there's no way to get that of a single symbol. So, proposition. Okay, let's extend this a little bit. Let's get an upper bound. So let x be as above. There exists an optimal code, which I'll denote C bar, which is prefix. Okay, for which the entropy is less than or equal to the expected code word length. So this is just the bound we've already got. Here's the interesting one, is that I can bound it above by 1 more than the entropy. Okay, so this says a few things in here. First of all, it's saying there exists an optimal code. So this, the optimal code must exist. I'm not getting any approximate. There is something which is attaining the optimum. Second of all, this optimum, there's at least one choice of optimal code, which is a prefix code as well. There may be more than one, but there is at least one, and it is prefix. So it's optimal among all UD codes, as we've defined optimality up there, and this one is prefix. And furthermore, then I have this inequality holding about that particular optimal code. Proof. So set Lx equal to the max of minus log to the base d p of x. So it's the ceiling of this. So take this, round up to the next integer. Okay, and note that the sum over x of d to the minus Lx is less than or equal to the sum over x of d to the minus log to the base d of p of x. This is just using the fact that Lx is slightly more than minus log px. So I'm just substituting that in to get an inequality, which is equal to the sum of the px's, which is 1. So I've got this inequality out, and I know this holds, and that, you notice, is the Kraft-Macmillan inequality. Okay. By Kraft-Macmillan, there exists a prefix code with these word lengths. Now, I'm not saying that Kraft-Macmillan gives me an optimal one, but Kraft-Macmillan tells me there is a code with these word lengths. Okay, and it's even prefix. By definition, minus log to the base d of p of x is less than or equal to Lx is less than or equal to minus log to the base d of p of x plus 1, because rounding up, you never add more than 1. In fact, I can go strictly less than, and I can put a strictly less than here, if I was being careful. Averaging over x gives the bound. So that tells me that there exists a prefix code which satisfies this bound, because I've constructed one. Now, okay, why can there's one thing I haven't proven in here. What is it? It's that there exists an optimal code which is prefix, because I've only proved that, well, I can construct a prefix code satisfying this bound. Well, we know that there's only finitely many codes, only finitely many inputs. You know you're never going to use a code which has crazy long word lengths. That was clearly not going to be optimal. So you can restrict to finitely many codes. If there's finitely many codes, there's got to be a best one. And so we know there exists an optimal code, and as soon as I give you any UD code, any uniquely decodable code, you can find a prefix code with the same code word lengths, which will also be optimal. So there exists an optimal code which is prefix. So we're just leveraging Kraft-Macmillan all the way. Okay. All right. So that's all. What I just said is spelt out in the notes, but that's basically it. You know you're never going to use a really long code. That's clearly suboptimal. In particular, if all of the code words had lengths above this, then it would never be optimal. So you can restrict to codes where there's at least one code word which is short enough. You can work down from there, basically. All right. So, where does this leave us? Well, it leaves us in this rather awkward situation that if this equality is satisfied, then we're happy, and otherwise we are much less happy because we're not able to really say much about the optimal code. So, what we'd like to do is to make our average code word length a lot closer to this lower bound. We know we're never going to beat it, but we can try and get very, very close to it. And Shannon's big idea, based on the asymptotic equipartition property, is to say, let's not worry too much about that. Let's look at coding longer blocks. If we code long blocks, then we know that we have regular properties. And so we're going to look at block codes. So what is a block code? Well, okay, we know we can do this. That 1 doesn't seem like it's going to be much. But in many applications, that constant of 1 is quite a big overhead. And if we can try and get down, reduce this upper bound and get close to the left, then we would be much happier. Okay, so the basic idea consider the x to the n valued random variable which is given by x1 through to xn. So I'm going to take n terms and encode them simultaneously. Okay? Where x1 through to xn are IID copies of x. Okay. Then we have a bound. Okay, let's think about this. Well, the entropy of this random variable, we've already seen, the entropy of n independent copies of a random variable is n times the entropy of x. That is less than or equal to the expected code word length for x1 through to xn. If I used an optimal code for this block, that would be less than or equal to, well again, n times the entropy of x plus 1. Okay, if I had something here which was optimal. So now I look at this for a moment and I say, hang on, if I divide this equation through by n, then what have I got? I've got a code which is including n symbols, and it's getting arbitrarily close to the lower bound because this becomes a 1 over n. The per symbol code length gets a lot closer to the lower bound. And this is the basic idea. So we get h of x is less than or equal to 1 over n xn (1 over n), and this sandwiches out as n goes to infinity. So if I can find an optimal code for a block, then I'm feeling pretty good because I'm getting arbitrarily close to that theoretical lower bound, at least on the per symbol code word length. Okay, so let's try and do this a little bit more concretely. So that actually is, if we formalize this, we could make a proof. But let's try and do this in a more concrete way using the AEP. Okay, so this is the source coding theorem, which is Shannon 1948. So if you're watching carefully, you'll notice this comes before we knew the Kraft-Macmillan inequality. So the proof of this that we've given depends on the statement of the Kraft-Macmillan inequality that we gave last time and going through this way, which is a more logical way of getting it. Shannon proved this earlier. Okay, what's Shannon's first theorem say? Let x1, x2, etc. be an IID sequence of discrete random variables with state space x. For every epsilon greater than 0, there exists an integer n, or natural number n, and a map C, which maps xn to 0, 1 sequences of zeros and ones, such that two things are true. Well, first of all, the induced map, which we could call C star, what does that do? This is what you get when I take the union over xnk for k equals 0 to infinity. So I'm allowed to encode an arbitrary length sequence provided the length of that sequence is divisible by n. Because I'm going to include in blocks of n. So if n equals 3, I can encode anything as long as its length is divisible by 3. Okay, so 3, 6, 9, etc. is fine, but 7, I just don't know what to do with that. I'd have to pad it out to get it up to a multiple of 3. So this is now a map from 0 to 1 star, given by, okay, so I'm going to take x1, x2, all the way up to xnk for some k, that's a natural number, and it gets mapped to C of x1 through to xn, C xn plus 1 through to x2n, c, well, I'll just, etc. up to c xk minus 1 n plus 1 all the way up to xnk. So I'm taking blocks of length n and encoding each of them and then concatenating that together. This is injective. That's the first statement. And the second statement is 1 over n times the expected length of c x1 through to xn is less than or equal to h of x plus epsilon. Okay, so in some sense this shouldn't be surprising to us anymore, given what we've done with the Kraft-Macmillan inequality, but Shannon proved this before we knew about Kraft-Macmillan. So he proved this just using the asymptotic equipartition property to get this out. And so we're going to present his proof. Okay, proof. For epsilon naught greater than 0, split xn into disjoint sets. So t epsilon naught n, the typical sequences, and the atypical sequences, then minus t epsilon naught n. Okay. Order the elements in t epsilon naught n and xn minus t epsilon naught n in some way, e.g. lexicographic order. Whenever I say lexicographic, that just means alphabetical order where my alphabet is 0 and 1 and 0 comes before 1. Okay? Okay, so we're looking at this. So by the AEP, remember what the AEP tells us. It tells us we can do this split into our typical and atypical sequences. There are, well, how many elements are there? There's at most, I should say at most, 2 to the power of minus n hx plus epsilon naught elements in t epsilon naught n. Okay, so I know there's not too many of those. We associate each with a string consisting of L1, which is defined to be, well, the upper bound of n times hx plus epsilon naught bits. So because there's not too many of them and I've ordered them, I can just count out which number they are. There's the 0th one, the first one, etc. I count them out. How many bits do I need to list the number? That many. That's how many digits I'm going to need to uniquely determine each of the typical elements. Okay, so that's using this many bits to enumerate all the typical sequences. Okay, similarly, associate each element of xn minus t epsilon naught n, so all the atypical sequences. Well, okay, we don't really know too much how many there are, but we could bound this just from how many strings we started with. So with a string of L2, which is n log size of x bits. So I know I could, this is really inefficient. I could label all the elements of my set using this many bits, and I'm just going to use that labeling only for the atypical sequences. So I've got it for typical sequences, I can do it using less elements. For atypical sequences, I just do a fairly crude encoding. Okay. Now define C of x, 1 through to xn as these strings prefixed by a 0 if x1 through to xn is typical, or by 1 otherwise. The result is clearly injective. So it's clearly uniquely decodable. I've just added a prefix. I've numbered everything. Okay, I've used this many bits. In fact, it's prefix because I've just everything in here has a string. They're all the same length, and then I've prefixed this with a 0 or with a 1 so that I know which group I'm going through. There we are. So I've now got a prefix code. Okay. So this is a block code. This code has expected length. So let's calculate the expected length. Expected code word length is equal to the sum over x in t epsilon naught n, so over the typical code words of the probability of x times L1 plus 1, length of a code word if it's typical, plus the sum over x in xn minus t epsilon naught n, the atypical code words of px plus L2 plus 1. That's just writing out the length of this code. Okay, so this is now less than or equal to the sum over typical codes, typical words, typical strings, whatever, px times, well, we know what L1 is, so that's n times h of x plus epsilon naught plus 2, because I've got a plus 1 here and a plus 1 somewhere else. Because I've got the ceiling here. Plus, well, the sum over xn minus, so over the atypical code words of px n log size of x, again, plus 2. All these terms are the same. All these terms are the same. So this is equal to the probability that x1 through to xn is typical times this quantity plus the rest, which is the probability of atypical times n log but now, what can I say about this? Well, I know this probability is small in particular. I know this probability is close to 1 and this probability is close to 0. In particular, I can say this is less than or equal to well, this is less than or equal to 1, so I just write n times h of x plus epsilon 0 plus 2. And this, we showed, is less than or equal to epsilon naught by construction. N log mod x. And in fact, I'm going to be a little bit clever. I'll bring the plus 2's together and say they're just a plus 2 overall. So if I bring the plus 2's out of this term and this term, they add together and you just get 2, and I just get these two terms. And I look at this and I write this is equal to n times h of x plus epsilon 1 for some value of epsilon 1. So where epsilon 1 is epsilon naught 1 plus log mod x plus 2 over n. Okay, so I've just got a big inequality. So what do I do now? For a given epsilon greater than 0, choose epsilon naught small enough that epsilon naught times 1 plus log of the sample size, the size of my space, is less than epsilon over 2, and n large enough that 2 over n is less than or equal to epsilon over 2. Put everything together and you get the desired inequality. So what does Shannon's theorem tell us? Well, it gives us a lot of intuition as to why a block code is a good thing. When we extend to a block code, we can restrict down to only doing something efficient for the typical sequences, and all the others we don't need to worry about. We can just encode them somehow. And Shannon's code shows us that if we do this, or Shannon's construction here, shows us that if we do this, we can get something which is pretty close to optimal. There are problems. The first problem is I've got to list all the code words in a length n block. So if I've got something of length n, well, let's say I've got something of the length 100, because I'm going to have to make n large enough to get a small error. So if n's 100 and my input is 26 characters, alphabetic, then the number of code words I have to manipulate is 26 to the power of 100, which is more than the number of atoms in the known universe. So while this is great, it's not so easy to work with, because I have to list all the possible inputs, sort them into the typical and the atypical, order them, record what code word I put with everything. It's a pain. And recording the code is a bit of a problem. Other things, well, this result, and in general block codes, they only work if the length of your input is divisible by the length of a block. So what do you do in practice? You take blocks and then at the end you normally pad it out. So you have some character that you're happy just to add on to the end of the string. So if I've got a block of length 3, I have an input of length 7, I add 2 null characters at the end, 2 things I don't care about, spaces, whatever, so that I get something of length 9 that I can encode. And so we do that. We will finish there and come back tomorrow to talk about some more practical codes that we can construct. And we will also hopefully then start seeing what happens when we do this computationally.